All right. So now that you've struggled a little bit with these questions, it's time to talk about the answers and the rationales that go with it. It says click about where the arrowhead of the force vector would threaten to cause the block to slide down the ramp. Obviously, that would be in the direction this way. So all you have to do is decide where the arrowhead is. Would it be way down here? Would it be right there? Where would it be? So imagine it to be coming out of the same point of origin as the blue gravity vector. So basically, the way to rationalize this is gravity's pulling straight down. We know that at all times. And since the ramp is at an angle, we can imagine that's the x-axis and this is the y-axis. And so this force vector could be broken up into components that look like this for the y and that for the x. So right there is the arrowhead, approximately where that would be for the x direction. So there'd be an arrow here and an arrow there. Hit next. Okay, click on the resultant of x2 and y2. So x2, that'd be this one. Yeah, x2 and y2. The resultant of this and that would be this right here. That would be the result. Because if you think about it, if this was just talking about movement, if you moved this way, like in a video game, you went to the right so many squares and then you went up so many squares, the result would be as if you moved along this diagonal. So that is the rationale. Okay, the resultant. So this question is basically trying to get you to acknowledge that you know what the word resultant is, for one. So let's click right here, but also be able to read these labels. Nice technical looking labels. Hit next. Okay, challenging. If 4.5 and 5.0 were the only ones in the scenario, so 4.5 and the one that says 5, okay, click about where the resultant of those two would be. So if this was there and that was there, this diagonal could be broken up into this and this. Therefore, if we break them up into this and this, we can kind of erase this in our minds. So that leaves nice perpendicular arrows. This one, and that one. Now this one is in the same direction as that. So we'd want to sort of pick it up and put it on top here. So that gets our height to about right there. So the answer, the arrowhead's going to be somewhere along, if you could imagine a dotted line here. We just don't know where in the x direction. The x direction comes from this because this is the only thing left. So that means we could put kind of in our mind a dotted line going up, and where those two dotted lines intersect, that is where the arrowhead's going to be. So once again, if I pick up this and set it right there, that gets me about right here. And then if I move over to line up with where this is, then this is about where I need to be. Next, click on the y component of the red vector. Okay, so this is the red vector, and the y component is this one. It's even labeled y, right? The red vector. Next, click on the vector that represents the force of friction. Okay, this is the person's force, and this is the force that's opposing it, right? You push on a cabinet like this and it's going to resist. You'll clearly feel it. You're pushing that way, it's pushing this way. All right, so there's that. And that's just me trying to get you to acknowledge that, you realize that this is the force friction. Click on the x component for the red vector. The one that's pointing up and to the right. Yeah, the x component is that one. Pretty simple. If the dark purple, talking about 9 and 5, all right, so 9 and 5 are the only ones in the scenario. This one's already, along, it's like vertical, perfectly vertical. 9 is not. So let's break this 9 up into its horizontal and vertical components. So if we, replace this diagonal with this and that, we can kind of erase this in our minds. So all that exists now is this, that, and that. And this happens to be about the same size as that. So they cancel each other out. Let's erase this from our minds, erase that. The only thing left is this vector right here. So that would be the resultant. Next. What is the force that's always perpendicular to the surface an object is resting on? I should put ing in there. That's the normal force. Yeah. And that should be easy to remember because it is very normal. It happens all the time. I'm sitting in a chair that's resting on the floor. There's a normal force pushing up. Gravity's pulling straight down. Normal force is pushing straight up. Otherwise, I would start accelerating downwards. If the force of friction between the block and the ramp turned out to be enough to keep the block from sliding. So in other words, the force vector in this direction is not bigger. It's basically equal to the force of friction is going to be in the other direction. And because I said if the force of friction turned out to be enough to keep it from sliding, then that means this is going to be equal to that. It's going to be able to withstand it. Click where the arrowhead would be. All right, so let's break this up into its vertical. That gets us about right there. And the horizontal is the one that we're actually interested in. That gets us right about there. That's the arrow that's threatening to drag the block down the ramp. And if the friction is going to be enough, it's got to be in the perfectly opposite direction. So that'd be mirror image, right? You can see that if the arrowhead, if this lines up with right about there, then we need to flip over to this side and click right there. All right, challenging. If all the solid resultant vectors were left to fight this out, where would the final result be? Okay, so this is represented by its x and y components, so we can erase this from our minds. All that exists for that is this and this. This can be represented as that and that, so that's gone. Erase this from our mind. So now all we have is this, 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 that, and that. And we just need to figure out who cancels who. This one clearly looks about the same size as that. So let's erase those. Erase. And then this takes away from that about that much right there. So that there's where the arrowhead would shrink. And this would be gone, and that would be gone. And now this would essentially, let's move that in our minds. Let's pick it up and move it over here. So that brings us to there. You could imagine a dotted line right here. And then where I said the arrowhead was for this, a dotted line like that. And where those two intersect is where the arrowhead would be, but it's not asking for the arrowhead. So let's play it safe and click somewhere in between, like on the actual vector. So that, because when I make these questions and I have to define a region, a rectangular region, I stop a little bit beyond where I think the arrowhead would be. So bringing our selecting somewhere in the middle is a little safer. All right. If the ramp is strong enough to support the weight of the block, about where would the arrowhead of the normal force vector be? Okay, so the normal force is perpendicular to the surface. That would be this way. So we just have to decide how far. And I said, if the ramp is strong enough to support the block, I said that so that you'd know that it is equal to and opposite to this. So the gravity vector gets broken up into its x and y components, and the arrowhead of the y component would stop about there. And that means equal and opposite. I'm trying to imagine mirroring that. So right about there. Click on the component vector for the absolute least magnitude. Well, this one, which is equal to that one because this is a 45-degree angle. So I defined this and that because they're both the same size. So I defined a rectangular region all along here because I didn't know which one of these you might pick. So, and I want both of them to be right, so let's just pick one of them. Where would the normal force in the diagram be? It would be up this way. So somewhere in the middle of, we already did this problem. The arrowhead would be there. So I'm going to click somewhere in the middle where it's safe. Click on the X component for the dark purple vector, the one pointing down and to the left. And I said X component. So that'd be, here's the down and to the left arrow, and this is the X component of that. Click on the vector that represents the force of the lady pushing on the cabinet. That's easy. According to the appearance of the vectors in this image, would the filing cabinet actually move? And what I want you to realize is that since this arrow is about the same size as that arrow, they would cancel each other out. In other words, this cabinet's not going anywhere. Challenging. If the components are labeled Vx1 and Vx3, okay, Vx1 and Vx3 are the only vectors, where would the arrowhead of the resultant be? Well, this would take away about that much of that one. So the arrowhead would be somewhere close to that area. Click on the vector with the greatest magnitude. That's just me trying to get you to understand that greatest magnitude is another way of saying the biggest arrow. That'd be this one. This diagram looks like represents a block on a ramp. That's why the X and Y axes, that's plural for axis, are tilted. That being the case, click on the vector that represents the force due to gravity. Straight down, that's this one. Click on the resultant of F1 and F2. F1 and F2. Pretty easy, because if you moved this way and you moved that way, the resultant would be moving like you went this way. So just click on that. Unanswered questions. Number 16. How did I not answer that? Have invalid answers. Question 16. Okay. How do we go back? I've never had to go back. 16. Did I not click on anything? I must have been talking. Oh, yeah, okay. Would this filing cabinet actually move? No. Next. Submit. Okay. Yeah. Auto grading. I love this quiz maker thing because it gives you instant feedback. You don't have to wait for me to tell you if you're right or wrong. And there you go. There's your answers. Just as I said. So now you can check your work and compare it to the logic that I provided in this video. Have a nice day.